Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will derive simple updating rules when the observation y is a random variable taken from a normal distribution with mean mu and variance sigma squared. By the way, we are assuming that sigma squared is known. Okay? We will consider a prior distribution that is normal with mean m and variance s squared. Let's begin. Okay, so let's try and derive those simple updating rules for this case when we are considering a single observation coming from a normal likelihood. As usual, right, we will start with the main two ingredients of a Bayesian analysis, right? We need the likelihood. The other one is our prior. Okay, so but let's talk about the likelihood first. Okay, so we know that we could think about the likelihood as conditional probability, if you will. The probability of observing a particular value of y given that we have information about mu, the mean. Okay, and again, note that we are assuming that sigma squared is known. Okay, so that's why we only have that parameter mu here. Okay, so we know that the probability density function for a normal with mean mu and variance sigma squared is given by something like this. First, we're going to have the normalizing constant, right? The constant that makes that the integral of that PDF to be equal to 1. Okay. So in this case, it is 1 over the square root of 1 over the square root of 2 pi times sigma squared, or you could re-express that like this: sigma times the square root of 2 pi. Then we have an exponential, right? 2. We are going to have the following power here: minus 1 divided by 2 times sigma squared times y minus mu squared. Okay. Okay, we know that mu could be any real number. We know that y could be any real number. Okay, and sigma squared, well, must be positive. Now let's try and simplify this using the proportionality symbol. Since we are assuming that sigma squared is known, right? Let me just point that out. Assumption: sigma squared known. Is known. Then that is just a constant. Okay, that term is just a constant. So our likelihood is proportional to that exponential. Okay. Okay. So second ingredient, our prior. So in this case, we are considering a normal with prior mean m and prior variance s squared. Okay. So we could just copy paste this and then modify that expression accordingly. That's exactly what we're going to do using our notation. So we have p of mu, right, is going to be, instead of a sigma here, the PDF for mu is going to be 1 over the square root of 2 pi times s. We are going to have an s here as well, and instead of mu we will have we're going to have an m here, right? Okay, so that's it. We have our first two ingredients. Just again, just like before, let's try and re-express this using the proportionality symbol. We know that, well, since this guy here doesn't involve mu, right, then we can ignore it for the analysis, right? Oh, and we should have a mu here, right? That's the variable here. Instead of a y, we have a mu. Excellent. Okay, so since again that term doesn't involve mu, we can ignore it. It can be absorbed here by the proportionality symbol, and yeah, so we just have that the prior is proportional to that exponential here. Okay, now as usual, right, in plain English we know that the posterior is proportional to the product of prior times likelihood. Prior times likelihood. So in this case, what we're going to have is the product of those two exponentials, right? So we're going to have this guy here times our likelihood for a single observation. Okay. Next, we know that we can combine those exponents. So let's do that to further simplify that expression. So let me copy this guy here, right? Something else. Note that -1 over 2, it's a, you know, a common factor. So we could factor that out. And here, let me re-express these two, right? What we have to do is we have to sum these exponents, right? And I'm just factoring out that -1 divided by 2. Let me do a little bit of algebra here. What we have is that first term here, this one, and then we have plus, and we have that second term here, and we're going to divide that by sigma squared. Okay, so just combining those two exponents. Okay. Okay, so then if you recall, we did something like this in another video, right? But let me just quickly remind you what you would need to do next, right? You could find a common denominator here. That common denominator would be the product of these two guys, right? So we would have s times sigma squared, right? Now if you do the math here, If you use that as the common denominator, you will have a sigma squared here multiplying the first term plus, and then you would have an s squared multiplying that second term. Okay, so these two expressions are equivalent. Okay, then you could factor out this guy, s squared divided by sigma squared. Right? And then you only have this here. Then what we did is we expand these two. Remember? Right? So we did a little bit of algebra with this guy. So that happens to be, right, once you expand, it's going to be the same as mu squared oops, sorry, not what I wanted to do. It's going to be just mu squared times s squared plus sigma squared plus, and then when you expand this, right, you are going to have mu squared minus 2 times mu times m, right? And when you expand this one here, you're going to have s squared times y squared minus 2 times mu times y times s squared. Make sense? So we did something like this before, so let me just quickly go over that. So after you expand, you're going to have something like this, and as we said, you're going to have a sigma squared m for the first one, and then you're going to have an s squared times y for the second one, right? And then you're going to have the other terms, right? In this case, you're going to have mu squared minus 2 times mu times m plus m squared, and then you would have m squared times sigma squared, right? So that would be the other term here. Oops. Okay, and the next one, right, is going to be just s squared times y squared, right? Make sense? So we have s squared times y squared. Got it? Okay, so that's just, after you expand that exponent that we have here, right? So once we do that, we could rewrite this, right? We have e to the negative 1 divided by 2 times s squared sigma squared times this, but this after the algebra is just this, right? Now note that this one here, since we're assuming that sigma squared is known, m is the prior mean and s squared is the prior variance and y squared is our observation, this, right, is going to be an exponential to some constant, right? So let me just be super specific, but the point is that we are going to be absorbing that last term that involves that exponential into the proportionality. We're going to incorporate that into the proportionality sign. So instead of having this here, we have the product of these two exponentials, right? You guys agree that that expression and that expression are equivalent, right? But as I pointed out, this last one here is just a constant. So let's absorb that one with the proportionality symbol. Okay, that doesn't have to do with our parameter mu, right? And remember that the one that we are after here is the oops, not what I want. The one that we are after here is the probability of mu, if you will, given our observation y. Okay. Okay. So then, if you remember something that we did, right, when we talked about obtaining the posterior distribution using that kind of prior, a normal prior, right, for a single observation, is this. The next step was we had something like this, right? So we completed the square. So to complete the square, it would be, you know, we would factor out that term here in the exponent, right? You would have something like this. You would have it here, right? And then you would need to divide by that term here. So we just factor out this guy. But if this one, yeah, no problem. Mu squared times this is the first term. But this one doesn't include that s squared plus sigma squared multiplier. So if you divide by that, you end up with this. So, and the next step, right, as I was saying, would be just completing that square, right? So, but we have basically that thing, right? We know that it would be the same as mu minus this squared. And again, note that this guy here doesn't involve the parameter mu. So what we're doing here, what we would be doing here is just multiplying by a constant, right? So that doesn't affect our posterior, right? It's like multiplying by a 1, that integral that you're basically doing, right? Okay, so let me just point that out, that what we did is just completing the square completing square. And again, we did this in more detail, right, when we talked about the posterior, but I just want you to remember some of the steps and to make it more natural, right, and also to justify why we're doing this, right? Here what we need is a square, right? Okay. Oh, I don't know why it won't let me. Let me just get rid of this. Copy paste again. So what I want is to place a square here, right? That's what we need, right? We just complete the square. We know that this would be the right term. We don't need this guy here anymore, right? So, and now something more, something that we did when we discussed that posterior. We said, you know, this is the same as this. Okay? Now, why that observation would be important? Because now, as we said, the expression that we're after is the probability of mu given our observation, right? It's a conditional probability, basically. So note that the variable here is mu. So what we have here is mu minus something squared, right? And we have minus 1 divided by 2 times something, right? So if we go back to the expression of your likelihood for a normal, what we have is the kernel of a normal. The mean is going to be this guy, variance this guy, right? So finally what we have is that our posterior distribution, and again we talked about those steps in detail, the posterior distribution is normal with mean. Let me call this guy mu star. Mu star happens to be this guy. And S star, well, S star squared, the posterior variance, would be this guy, right? S squared times sigma squared divided by S squared plus sigma squared. Make sense? Just, you know, by comparing the PDF of a normal with our expression for the posterior. Okay. Now that we recalled these expressions here, and also that's why I wanted you to, you know, I wanted to refresh your memory as to what you have to do to obtain this. Is, well, if you want to do this quickly, it is not that quick, right? Before, with binomial likelihoods and Poisson likelihoods, doing something like this, just the idea of posterior is proportional to prior times likelihood, then it was very straightforward to obtain the parameters of the posterior. But in this case, well, it takes a little bit of work, right? And we didn't even talk about all the details here. We did it in another video, but even here, just having a general idea of what to do, it takes a while, right? So that's why we want to, in this case, in the particular case of a normal, have those updating rules very clear in our minds, right? Okay, so to introduce these updating rules, these rules that will give us the parameters of the posterior more quickly, let me introduce a new concept, the concept of precision. Okay, so precision. The precision is the reciprocal of your variance. Okay, so you could have a prior precision and a posterior precision. Okay, so in this case, posterior precision would be just 1 over s squared. Okay, 1 over s star squared. Okay, that would be our posterior precision, right? And note that, well, that guy would be just the reciprocal of this guy, right? Okay, so let me write that down. It would be just this divided by this. But note that that would be the same as just this, right? We have a common denominator there. So s squared plus sigma squared divided by s squared times sigma squared is the same as this, right? But if we have this, we can simplify, right? It turns out that the posterior precision would be, if we divide by s squared here, I mean, these two guys cancel out, and these two guys cancel out here. So let's do that. So once we simplify, the expression that we will have for our posterior precision is just that. Right here, we cancel out the s squared, and here we cancel out the sigma squared. Sense? Okay, so that's our posterior precision. Note something interesting. The posterior precision is your prior precision plus the observation precision, right? Because that's the variance of your observation y. This one is the variance that you are attaching to mu, your parameter, right? Okay. So bottom line, posterior precision equals prior precision plus observation precision. So it's easy to remember that. Okay, now let's talk about that expression for the posterior mean. Okay, posterior mean. Posterior mean. So we have that. Okay, now let's try and rewrite that expression here. Note that this guy is a common denominator. So let me express this one like this. So I'm going to have a sum here, first term and second term. Make sense? Clearly those two expressions are equivalent because this guy is just, common denominator. Okay? Okay. Now, you guys remember that what we have here is that s squared, well, s star squared looks like this, right? And that the precision, the posterior precision, is equal to s squared plus sigma squared divided by s squared times sigma squared. Right? Yeah? Are we clear on that? Okay. So, what I'm going to be doing here is, see, we have s squared plus sigma squared here divided by s squared times sigma squared. Can you see that we have that here, s squared plus sigma squared? So if we divide by s squared times sigma squared our numerator and our denominator, what we're going to be doing is we are going to make the posterior precision magically appear there. Okay, so that's what we're going to be doing next. We're going to be multiplying the numerator and denominator by that quantity. Okay, here we go. So let me divide here by s squared times sigma squared, right? S squared times sigma squared let's do the same here. Let's do the same here, and we're just, you know, multiplying by a1 basically. So we're not doing anything illegal, but once we have this, right, we have our posterior. This guy here is our posterior precision, right? And our posterior precision is also equal to this. So let me use this instead for the denominator. So here, what I'm going to have is just 1 over sigma squared plus 1 over s squared. Okay? Not what I want, sorry. Well, yeah, let me change that. So I want 1 over sigma squared plus 1 over s squared, because that's also the precision, right? That's the alternative expression for the precision once you have simplified this one here, right? Now note something interesting here. We have sigma squared times m divided by s squared times sigma squared. So these guys cancel out, right? Okay. Now again, s squared plus sigma squared divided by s squared times sigma squared is the posterior precision. But once you simplify expression of the posterior precision, you have this. So let me use that one instead, that alternative expression for the posterior precision. Now you have an s squared multiplying, you have another s squared dividing. These cancel out. There you are. Finally, let me rewrite this. That expression happens to be the same as 1 over s times m. This one happens to be 1 over sigma squared times y, and that is our m star, right? Our posterior mean. So let's summarize what we have here. Note something really interesting here. The posterior mean happens to be a weighted average, right, between your prior mean and your observation. Okay, makes sense? And what you have here is prior precision divided by posterior precision times prior mean. So you have a correspondence here. This is the precision of your observation divided by the posterior precision. Something more. Note that these weights, the sum of these weights equals 1. So this is a proportion, and this one is also a proportion. Make sense? So it's a weighted average where you have these multipliers being the proportion that you assign the weight that the prior mean is going to have and the weight that your observation is going to have with respect to the posterior precision. Make sense? So it's so much easier to remember this than trying and do, all the algebra again to come up with the expressions for these parameters of your posterior. Okay, so let's summarize what we have here. That's the point of this video. Your posterior precision happens to be prior precision plus observation precision, right? That's your posterior precision, and the precision is just the reciprocal of your variance. Okay, and then once you have that guy, your posterior precision, if you want to find the posterior mean, m star, all you have to do is prior precision times prior mean divided by posterior precision. Observation precision times observation divided by posterior precision. And that's it. Okay? Well, thank you so much for watching. Please take care and keep working hard. See you next time. Bye.